Our next speaker in this block is Laura. She's a PhD student in biomedical data science here on campus, and she's going to talk with us about parent-child interactions. Laura, thank you.
So, hi everyone. My name is Laura. I'm a PhD student at Stanford, advised by Serena Young. So it's a little bit of a deviation from what we just saw, but it has a lot to do with the topic. So how can we understand the idea of parent-child interactions from video? So if we see a scene like this, and we see a parent and a child interaction, actually for humans it's pretty easy to identify many cues that are hard for automatic methods. So is the mom looking at the child? Yeah, we can see that. Her mouth is open, she might be speaking. The child's head is in direction of the mom, so are they paying attention to the mom? The body language, are they paying attention? Are they touching? What type of interaction is this? And the objects in the scene also give us cues of context of what it might be happening in the scene. So all of these types of interactions and features are useful for child development specialists to try to test their hypotheses on how do these parent-child interactions go. As you can expect, this is not very scalable. It takes around 3 hours to annotate a 10-minute video. So this limits the diversity of data and cohorts we can, child development specialists can test their hypotheses on. And it's usually done on video. So it's not one image, you have to do it for a whole sequence of frames. And you want these very minute and fine-grained interactions for all of these frames. So this is where computer vision and our lab's work come into play. How can we automatically extract meaningful information from these videos to be able to help the child development specialist to do their work? This is also interesting for us as computer vision specialists because it's a complex task. There are many unsolved questions that we want to address. So how do we even represent the scene? It's real data, so how do we manage the noisiness that is reality? It's video data, we need to be efficient. It's protected data. How can we ensure protection and preserve privacy? And the annotations, as we saw before, they're costly, they're hard to do. So how are we going to work with this sparse supervision signal we have? So first I'm going to talk about how do we represent the people in the scene. So we work with a particular family of models called human mesh recovery models. So these models take a single 2D image, and from then you predict a mesh model for each person. So you get the shape, the pose, and the location of the people in the image. And you can see here an overlay of what that could look like. But also if you go to the next image, the top view, you're seeing the value of this representation is that we can see the prediction in 3D. So we can know that if sometimes in 2D someone appears close, they could be interacting, but actually in 3D we know that they are not interacting. So this is important for all the features we talked about before. So it's also useful because it gives us a notion of interpretability. We can actually view and see if our predictions match reality. We can extract behavior from them and the other attributes I told you about. So how can we use this in real data? So real data of children is protected. It's hard to get for a reason, but child development is a great field, and they've been working for so many years. This is a data set that was collected, the Ceilings data set, for language understanding, and we repurposed it for our project. So we have video and audio recordings of 44 parent-child dyads interacting in their homes, and it's 1 hour of video for every month the child is 16 to 17 months of age. So we can actually track a child through time and follow them and see if we can learn how they grow. The data is noisy because it wasn't meant for this. So sometimes the camera is filming nothing. Sometimes there's like additional siblings and they just jump around. It's a challenge to deal with real data. So this is the model we've been developing, Harmony. It's a project that was ongoing in the lab because it's a hard problem. So I jumped into the project as soon as I saw it. And what we do is we're based on this idea of the 3D mesh estimates. So you take a video, you take each frame and predict the mesh estimate for the frame. Then you have this notion per frame, but these are processes that happen across time. So how do we know that it's the same person? We do something called tracking. So we match this representation across time, and we have a tracklet. Now that we have this time-wise representation, what do? We can compute the visual features based on the meshes. So this is an example of 3 features based on meshes, and it's what I was telling you about before, how interpretable the data is, right? We can see the meshes, and we can see they are not touching. So something as simple as a threshold that doesn't need supervision signals can be used to determine the attributes. We use these features are determined with help of our child development specialist collaborators. We don't know what we're looking for, and they know what they want. This is a brief demo. It could be nicer. We're working on this. But it's the idea that we were successful at having a first version. It's not perfect, but it allows us to extract some of the features that are of interest. It's viable. We can do 3D mesh estimation and HMR for this. And we also learned that we can replicate some behavioral things that happen across time when the child grows. We will release the code so anyone in the child development field can use it for their own videos, and hopefully we'll continue improving it so they can use it in bigger and better studies. So the next thing I want to talk to you about is something we realized when doing this work. There was a challenge that our methods were just not able to handle. So this is what we're doing now. How can we manage close interactions? So close interactions are basic for parent-child interactions, actually. They happen all the time, and they're the main characteristic of how a parent and child interact and how you can see they grow. So for example, if you have a baby, a small baby, they will likely be very near the parent a lot of the time. But as they grow independent, they start leaving and going through the world. So tracking how this close relationship changes is actually very informative. This is not the truth. If you just take adult-adult interactions, you can't just think this is a model for what happens with parents and children. It just doesn't replicate. So this is just an example of what happens if you take the interactions and assume they happen with children. They're different, so they have to be studied as something different. What we're seeing here is an example of a state-of-the-art method called BEV, and its predictions on an image of a parent and a child, or 2 people interacting. And from the camera view, we can see that it kind of resembles what we can see, and it matches, but then from the top view, we know that we were expecting the meshes to be embracing, and they're not that close to be actually embracing. So this is the truth. HMR methods can't capture close interactions yet. So that's what we're working on. There's not a lot of data in this space, and even less with children. So we're trying to set up a whole data annotation pipeline and system to have this happen. This is a preliminary result of our method, and it modifies somewhat an adult-adult interaction method, but it focuses on how we can think of these as separate interactions. That has been, I think, my main learning in diving into this space. Like, children are their own thing, and they're special, and they should be handled as something different and interesting in of itself. So here we can see from the camera view, they look like they're embracing, but from the top view, they are actually embracing. So the identification of downstream attributes from these meshes will be correct. And that's mostly what I brought you today. Yeah, I went a little faster than I expected. So I just wanted to leave you with the idea that this is something that I've learned from being in this space. What other things can we actually learn from children? If we don't think of them as like tiny adults, they're their own wonderful, different thing. And thank you for listening. This was a work with my lab, the Marvel Computer Vision Group, advised by Professor Serena Young. We have great collaborators, and I had some great funding sources. So yeah, thank you.